In our previous video, we reviewed how one calculates the regression coefficients, the slope and intercept, in simple regression. Now, let's go through an example using some survey data to illustrate how we calculate and apply the regression coefficients. This survey data is a small subset of cases from a larger data set published on Nate Silver's website 538, and I've modified the scaling slightly for this example. Okay? The survey rated how positively people rated the movie Empire Strikes Back and how positively they rated the Star Wars character Jar Jar Binks. Now, if you're not a big Star Wars fan, it may help to know that Empire Strikes Back is seen by many serious fans as the best of the Star Wars movies, while Jar Jar Binks is seen by many as the most annoying of the characters in that galaxy far, far away. So for this example, let's predict how people viewed Jar Jar Binks based on how they rated Empire Strikes Back. Now again, this is just a small slice of their data as an illustration of how to do these calculations. Here's that small subset of the survey data for our example. First, we calculate the mean for X, ratings for Empire Strikes Back, with higher scores indicating more positive views, and the mean for Y ratings of Jar Jar Binks, with higher scores indicating more positive views. We then calculate the deviations for X by subtracting the mean from each Empire rating, and the deviations for Y by subtracting the mean from each Jar Jar Binks rating. We then calculate the sums of squares for X and the sums of squares for Y. We also calculate the square root for each of these sum of squares. And we also need the cross products, so we multiply each person's deviation for X by their deviation on Y and add up all of those values. We previously covered how the correlation coefficient is the sum of the cross products divided by the square root of the sum of squares for X times the square root of the sum of squares for Y, which in this example is negative 10 divided by 4.87 times 3.742, which is negative 0.549. Now, if we wanted to calculate the standard deviations for X and Y, we could calculate B1, the slope of the regression line, by multiplying the correlation by the standard deviation of Y divided by the standard deviation of X. Alternatively, if we're calculating by hand, we can save a few steps and calculate the slope by dividing the sum of the cross products by the sum of squares for X, which in this example is negative 10 divided by 23.714, or negative 0.422. B0 is then equal to the mean of Y minus B1 times the mean of X, or 3 minus negative 0.422 times 3.571, or 4.506. The predicted score when X is equal to 0 is 4.506. Okay, so we have the slope and the intercept. Let's make a graph of the data and the regression line. Let's start with making our grid for the data points. We'll put Empire Strikes Back on the x-axis because that will be our predictor. And we'll put the Jar Jar Binks ratings on the y-axis because that's our outcome. We then add the data points for each person, and we can see the negative trend that was apparent in both the negative correlation coefficient and the negative value for the slope. Now we'll add the regression line. A trick for drawing the regression line is to simply calculate the predicted y's at both ends of the x-axis and then draw a line between them. For example, we already know that when x is 0, the predicted y is 4.506. Remember, it's the y-intercept. And when x is 6, the predicted y is 4.506 plus 6 times negative 0.422, or 1.974. We then draw a line between these two predicted values and we have the regression line. Remember that we previously noted that the point of averages, that point that is the average of x and the average of y, is always on the regression line. Well, the average Empire rating was 3.57 and the average Jar Jar rating was 3.0. So yes, we do see that the point of averages is exactly on the regression line. Okay, so let's use the regression line to predict how they would rate Jar Jar Binks if they really didn't like Empire Strikes Back and only gave it a rating of 1. We'll take the regression equation and plug in 1 for our value of x. So our predicted Jar Jar rating is 4.506 minus 0.422 times 1, which gives us a predicted Jar Jar rating of 4.084. That corresponds to the point on the regression line for a score of 1 on the x-axis, the Empire ratings. Now, remember this predicted value of 4.084 for someone with an Empire rating of only 1. We'll come back to it later. Understandably, our predicted scores won't be exactly correct. The difference between reality, the real score someone has, and the predicted score based on the regression equation is called a residual or just an error. Mathematically, we write that as the residual is equal to y sub I, or the observed score for person I, minus y hat sub I, or their predicted score. Y with the little upside down V on top is called y hat. It's just statistical shorthand for the predicted value of y. There's an old joke. Two statisticians are talking and one asks, why hat? And the other replies, because it's going to rain. You don't see many statisticians doing stand-up comedy. Okay, you'll also see the residual represented by E sub I, again, which is just a shorthand for the residual or error for person I. Now, think back to our discussion regarding the mean. Remember, the sum of the deviations from the mean is always equal to 0. That was one of the fundamental characteristics of the mean. Well, the same principle applies to our regression line. The sum of the residuals around the regression line is equal to 0. The positive and negative deviations ultimately cancel out, whether we're talking about deviations around the mean or deviations around the regression line. Similarly, remember that the sum of the squared deviations around the mean is a minimum. Deviations from any value except the mean will always result in a larger sum. That same principle also applies to our regression line as well. The sum of the squared deviations about the regression line is always a minimum. Deviations from any other line will result in a larger sum. Because of this, we technically refer to this as least squares regression because those squared deviations are as small as possible. Any other line will result in a larger sum of squared residuals. So that wraps up our example of calculating and graphing the regression equation in simple regression where we have a single predictor variable. In our next video, we'll delve a little deeper into the regression model and revisit the concept we saw in ANOVA, partitioning the sum of squares. Can't wait. Until then, bye.